And welcome back YouTube to our Radiation Heat Transfer Learning Journal. So in the last video, so we're gonna have this two flux model trying to make this third set of equations. So yeah, I already explained to you what this two flux model means. Like for mu equals 0 to 1, okay, or mu positive, it will be a certain I, okay? So we call this I plus, because I is going in this so-called positive direction, right? So we can call this the positive direction. And in the other direction, we'll just call it, if mu is in the other direction, meaning you're going backwards towards the origin, then like if this is your starting point and you're going this way, then I'd say, yeah, that's a negative. So we call it the we call it the I minus here. So this is why it's called a two flux model, because when you have this set of angles, you have one representative flux, or one representative heat flux, so to speak, or intensity, and you go in the other direction, you have another representative heat flux. Now, how does this then generate our third equation? Well, what we do is we try to substitute this definition of I into here, where we talk about our moment, right? So we try and substitute our definition of I, okay, which takes a value of I plus from mu equals 0 to 1, and I minus from mu equals -1 to 0. So we can kind of split up our integrals into two parts. One is where mu is from -1 to 0. One is where mu is from 0 to 1. And doing that, we have here we'll substitute I minus, and here we'll substitute I plus. Alright, and since it's constant over this range of mu from -0 to 1, the intensity remains constant, and likewise from mu equals to -1 to 0, it remains constant, and 0 to 1, it remains constant, I plus and I minus here. So you can just factorize the thing out, and once you do that, you make this part of the integration rather simple. And as you can imagine, you don't only need, you can do it with a two flux model, or two flux model kind of makes sense, though of course you can do a 3 flux, 4 flux, 5 flux, or 6 flux even. So you can actually make many more equations like so, but 2 flux is just the simplest way of doing it. Okay, so now that you have this over here, these two integrals here, it becomes rather simple. Okay, you just substitute the integral in here from 0 to 1, and after you do all this substitution, you do the integrals stuff, your equation reduces to something rather simple. Okay, so we will have ik equals to 2 pi k plus 1 and I minus 1 to the k plus I plus. So this is our two flux model representation of the moments. Alright, we had these two equations, so we needed one more equation. So let's try looking at our second moment equation. So I2, okay, let's take a look at I2. Let's substitute k equals to 2, so we get I2. So we substitute k equals to 2, and this is the result. -1 squared, -1 to the power of 2 is just 1, and then we have k at the bottom, which is 2, and that will actually result in I2 being 2 pi over 3 I minus and I plus. So this is half of our third equation. Now it's like, okay, great, we just introduced 2 more variables. What are we going to do about that? Well, we'll notice something a little special. You see, when you have even k, that means k equals to 0, k equals to 2, k equals to 4, the I minus term here is always positive. So you have a positive I minus here whenever k is even. So when k equals to 2, k equals to 4, k equals to 6, k equals to 8, the terms inside this bracket remain constant. It's a I plus and I minus. So we're going to exploit that and take a look at k equals to 0 case. So we can do k equals to 0, just like what we did before. Substitute k equals to 0, and we'll find that it is just 2 pi I plus I minus. Now take a look at the inside terms. Because now they are exactly the same, we can sort of equate I2 to I0. I mean, provided we have some sort of factor, so we can make I plus I minus and I plus the subject. So I minus and I plus equals to I2 over 2 pi over 3, and then I plus and I minus added together, it will be I0 over 2 pi. Okay, so combining these two equations together, this one and this one, we get our third equation here. Our third equation here is I2 equals to I naught over 3. So this actually makes our third equation over here. So with that, we can solve with the proper boundary conditions. We can solve our set of PDEs using some, because this very much looks like diffusion, self-diffusion type equations or conduction kind of equations. So after that, solving becomes relatively simple. We have done away with the whole angular dependence term by making a few simplifying assumptions and by doing these integral things, thereby getting our moments. Alright, suppose with me you solve all of that. What are we going to do with these moments? Suppose you know I2, I1 and I0. What then are we going to do? So I want to bring to your attention some interesting properties of I0 and I1, the 0th and first moment. So I0 actually has a very important significance here, because and you'll be wondering why we add the 2 pi in front. This 2 pi actually makes I0 identically equals to G. G is this integral of the radiative intensity over all solid angles. And likewise, if you want heat flux, you take the first moment, 2 pi integral from -1 to 1, the intensity mu d mu, and that equals to the heat flux. Now remember I said before, you don't need to know your full intensity field. You don't really need to know your full intensity field per se. All you need to do is, at the end of the day, you just want to calculate heat flux. That is the goal of heat transfer. You want to calculate some sort of heat flux. So as long as we find out I1, that is enough. Okay? So now that we know that I0 is actually this G term and I1 is this Q term, we can rewrite our equations. Where is it? Yeah, we can rewrite these two equations in terms of G and the heat flux. So that makes our job way easier. Okay? And of course we can replace I2 out with this term here. We can replace I2 out with this term here, and thus that makes our job also pretty easy. So but when we substitute these relations here into these equations, we will get the following. Okay? So first things first, we can get rid of I2. We substitute out I2. So I2 is actually equals to I0 over 3. So we substitute I2 into this equation here. Thereby we get this equation over here. d I0 d tau lambda equals to -3 I1. And we have this other equation here as well. Alright, we have this other equation here as well, which we did not touch. Alright, so this become 2 couple ODEs, with tau lambda being the only variable of interest. Okay, so like I said before, we substitute these two quantities in. So at least now it looks to us that hey, this equations actually have some kind of physical significance. So at least we're not talking in abstract terms like moments and all, but we're talking about heat flux and we're talking about G, the incipient radiative intensity. So yeah, basically we just solve for this. So now we have a set of 2 equations that are pretty simple to solve for let's say a 1D case. No, even for 1D case we went through a lot of work, but at least we got out the angular dependence by switching around our radiation equation and simplifying it into these two equations here. And this very much looks like diffusion. Okay, so what boundary conditions shall we use? If the boundaries are gray in general, we can use radiosity as the boundary condition. So at tau equals to 0, I plus equals to J1 over pi, and that's how we relate radiosity to this intensity. Okay, and likewise at the top plate, okay, so J1 is the radiosity of the bottom plate. At the top plate we also have some certain radiosity, and I minus equals to J2 over pi. So how we relate radiosity to intensity, we talked about it before, or at least we've gone through the concept of how to get it in the earlier videos. Yeah, because intensity and the heat flux, they are kind of related by the angles. Okay, so intensity is on a per solid angle basis. That's why you have a pi at the bottom there. Okay, so next one. So now we see this I mean, if you want to write G in some other sense, okay, because we now put things in terms of I plus and I minus, so we kind of want G in terms of I plus and I minus again, and Q, the heat flux, in terms of I plus and I minus, so that we can substitute our boundary conditions in here. All right, so in terms of J1 and J2, which we assume are known, so we want to make this Q and G in terms of J1 and J2. Okay, so I plus will be in terms of J1 over pi, and by doing so, if we do the substitution that G is 2 pi I plus I minus, Q equals to pi I plus minus I minus, we use that, we will get these equations here. G plus 2Q equals to 4J1 at the bottom plate. So this is how we so-called can write our boundary condition, in one way of writing our boundary condition. And at the top plate, G minus 2Q equals to 4J2. So this is another way we can so-called write our boundary condition. In terms, if we want to eliminate I plus and I minus, and just have G plus 2Q in terms of J1, G minus 2Q in terms of J2. So this is at the two plates. Okay, one is for the colder plate. Alright, one is for the colder plate here. Alright, at the bottom plate, which we assume is hotter. One at the top plate, which we assume is colder. Of course, it doesn't matter if the hot plate or bottom plate is hot or cold respectively. Top plate or bottom plate is hot or cold or hot respectively. You just have a different sign convention for the heat flux. Okay, you have a different sign convention for the heat flux, which will automatically take care of that. Okay, so with this you can essentially solve for the intensity field by doing some differentiation, but it's not completely necessary. So it's better, since we know this already, we can just solve for G and Q, and that's pretty much all we need. And likewise, if we know G tau and Q tau, we can sort of manipulate these equations to solve for I plus as a function of the optical distance from either plate, and I minus as a function of optical distance from either plate. Okay, so that is about how we get our I plus and I minus. Okay, so yeah, so that is for a 1D plate in general. It is a very simple way of looking at a heat transfer. It is a simple way of looking at the moment method. Okay, so but the question then becomes, how do we generalize it into something that is 3D or higher? I mean 2D or higher. So we only deal with the 1D case, and we need to do a lot of work, but for 2D case or 3D case, we will need to do even more work. So How do we actually do that? That there is more discussion in that aspect, but we can talk about that in the next video. Thanks for watching. I'll see you guys again. Bye bye.